Well, hello, my friends. Welcome to Marshable Math. We're in the full midst of the coronavirus 2019, the COVID-19 virus. So I thought it would be appropriate to discuss some exponential and logarithmic modeling that maybe you've heard about in the news and such like that. So I put this little exploration here together. Let's actually see how it does. Okay, so from what I've read, the Corona-19 virus doubles at a rate of every 3 days. So my question then is, what does the growth rate look like over time? So if we're going to build an exponential model, the model, if you remember, is going to be y, that would be the output, is equal to the original value a multiplied by some base, then to an exponent. So basically, we're going to be repeatedly multiplying a by b, and the exponent x tells us how many times we're going to multiply by b. So if we're doubling it, we're then multiplying it by 2. So this actual model, and let's just start with one. Start with one, say, infected person. So the model would look like this: y is equal to 1 times 2 to the x. And if it doubles about every 3 days, then x is equal to, say, the number of 3-day units. X isn't the number of days itself, it's the number of 3-day little packages or 3-day units. So if we just run it from the beginning, so when x is 0, how many people are infected? This is x over here. Let me just go ahead and say this is 3-day units, and this is number of people that are infected. So at time 0, x is 0, I would get y is equal to 1 times 2 to the 0. And 2 to the 0, we know that that's 1, so I just get 1. Of course, you start with 1, so yeah, I mean, the math works out. Now, after 3 days, we've got it doubled. So after one 3-day unit of time, I would then have 2. That would be y is equal to 1 times 2 to the first, right, which is 1 times 2, 2 total. And then we just start to double it every 3 days. So after 2 3-day units, after 6 days, I'm going to have 4. After 3-day units, 3-day units, that would be 9 days total. I would have then 8, and so on and so forth. So take a moment here and pause the video and just run the numbers yourself. Probably the easiest way is just to keep multiplying everything by 2. Get a calculator, type in like 8 times 2 equals, and then write that number down. And then type in times 2 and equals and write that number down, because it'll take the previous answer and multiply it by 2. And just run it all the way through until we finish out the table. You think I'm joking, but I'm not. Go ahead, but press pause on the video, stop and do that. Let's see if you get the same thing I do. I'll wait a moment. Okay, so here's the numbers that I've got, and I'm just doubling. So that would be then 16, 2 times 16 is 32, 2 times 32 is 64. I got to think rather than talk. And then that would be 128, 256, 512, then 1024, and I'm at the point now where I need to pull out a calculator. 2048, 4096, 8192, 16,384, 32,768, 65,536. I am just doubling. 131,072, 262,144. That's gross. And then 524,288, and then 1,048,576. Holy smokes! After 20 units of 3 days, which would be how many days total? after 60 days, you've got like 1 million people infected. Yeah, that's exponential growth. It's not even a parabola where it's just squaring. It's doubling, 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 doubling. Starts out very small, like a whole lot of nothing for quite a while, and then all of a sudden, pow, it takes off. So let's see if we can graph this now over here. Let's do, oh, how many grid squares have I got? Have I got 20 grid squares? I think I do. So down here it's going to be time, and this is going to be 3-day units. Starting at 0. Hey, it's a quarter past the hour. So then that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There we go. And then over here, this would be on the y-axis, would be the number of people that are infected. And like, how do I start it? Obviously, if I start with 1, I'm going to hit like 1 million. So what do you want to go with? You can't go by. You can't go. Well, every grid square has got to be the same amount in order to get an actual real look at the picture here. Go by 2s? No. Go by 100s? No. Let's go by. What did I write down? I'm going to go by 10,000s, I think. So this right here is going to be 10,000. 20, 30, 40, there's 50,000. 60, 70, 80, 90. This right here then would be 100,000. 10, 20, 30, 40, 150. 150K, K for kilo, which is 1,000. 60, 70, 80, 90, right here, 200,000. Oops, another 0. 200,000. I'm not going to get to my million mark, but golly, that's a lot. Okay, so let's plot it. 0 would be 0. I'll do the graph here in red. 0 would be 0. Where does it even come close to being visible at 10,000? Like after 10 days, you're at 1,024. Isn't that a tenth of 10,000? So after 10 days, 10 days right here. Oh, maybe a tenth. Is that a tenth? That looks more like a fifth. I'll call that a tenth. Somewhere in here we've got 10,000. So a day 13, 8,000. That's like 8/10. So day 13 now, it's almost 10,000. Okay, 14. Oh snap! Look at that. 14 is 16,000. So 16,000. If that's 10,000, 20,000, 16,000 is a bit more than halfway right there. And then 15 is 32. So 1, 2, 3, and then 2. And then day 16 is 65. So over 50, 65 right there. And then day 17 is 131. So 17, there's 100, 10, 20, 30, almost right there on that line. Right there on that line. That's 100,000, 10, 20. This is 130. Okay. That line right there. Are you following what I'm doing so far? Are you starting to see the big picture? Is that all I can plot? Day 18 is 262,000. Yeah, that's off my scale. That's like day 18. Woo, way up here. Okay, so what is this? Well, it's not 0, but it goes along pretty close there. It's not even recognizable when we're talking those big numbers. And then all of a sudden here, it starts to kind of really sort were to take off, look at that. Just like, wow. There it goes. Exponential graph. Yeah, that's why it's important. You're probably watching this video after some, the news events have kind of gotten up into full speed. But when they are asking people, yeah, you need to stay home, or you need to not be in groups of 10 or more, or whatever the kind of the recommended restriction is, yeah, because when this thing doubles every 3 days, after a while, what is this? After 2 months, we're up to 1 million people. Now, there are some things that would slow that, like obviously, if I'm infected and then I infect somebody else, they then cannot infect me back. So you've got to only infect people that are not, they've got to be in contact with people that are not yet infected. So that's why it's like, okay, stay at home, don't get out, don't talk to people. If we can suppress that or get a handle on it, we're not quite sure exactly what the details of this virus are, which is why there's so much alarm about it. Maybe it doesn't do much more than the regular flu, but then again, maybe it does. So the next question then would be, when will there be 10 or 100,000 people infected? Well, okay, so what does that mean? We've run this model now, y is equal to 1 times 2 to the x. And we've had the input be x, and we've had the output be y. This tells us, if we tell you how long it is for the time, this then will be the output. This will tell us how many. Okay, but this question then turns that around. This question says when, which is a time. So this question is saying, when is the y value 100,000? Well, okay, so if y is equal to 1 times 2 to the x, it's asking after how many days, oops, too many commas, and I'm going to drop the 1, just 2 to the x. How do you solve for a variable in the exponent? Well, what question has as its answer the exponent? And if you said log, you're a good student. So what this really means is this. Here's what I've got to do. I've got to rewrite it as a logarithm. Log base 2 of 100,000 is equal to x. I got to figure out the exponent on 2 that gives me 100,000. Now, if I go back into my table here, it's not going to be a whole number. If I go back in my table, 100,000 is somewhere in here because it's 65,000 and then it's 131,000. So if 100,000 is there, then it must be the input value for that, the x value for that, must be somewhere between 16 and 17. So between 16 and 17 units of 3, which, oh my goodness, I'm so embarrassed. Where's my calculator? So let's see here, between 16 times 3, yeah, 48. Golly, I'm embarrassed about that. 48, between 48 and then 51 days. Well, if that's like, 100,000 people is a lot. Well, I grew up in Wichita, Kansas, and it was like the population in Wichita was like 300,000. So a third of the population of the city that I grew up in, 48 to 51 days. And that's a little over a month. And so as of this videoing, we're a little over a month from kind of when it first started to hit the news. So yeah, that's why there's so much concern, and that's why there's an effort to kind of slow this down. How do you stop this? Eventually, obviously, it won't go on forever. Eventually, you run out of people to infect, right? So that's not really going to happen. Maybe you've seen a graph that looks something like, where have I got some empty space? You've seen, I'll just do it right in here. You've got a graph where it would look something like this. You're going to have it's exponential up into a point, and then it kind of flattens off and then tapers off because it's kind of run its course. And so there's talk then about, well, we don't want it to get this high right there on the number of people. because it would overwhelm the medical community. So what we want to do is we want to kind of, I've heard them talk about flattening the curve out, so it gives us a little more breathing room in terms of using people or getting people into medical facilities to help them out with ventilators and things like that. So yeah, exponential thing is no joke. Doubling, well, that's not a big deal. Well, it is after a while. So exponential functions and logarithms, yeah, they're useful. If we can use this to model a biological outbreak and then have some idea of what to do to reduce it or contain it and so forth, that's great. And that's the power of mathematics. It's not just random chaos, or it's not just some kind of magical powers that we don't understand. If we can actually organize it, describe it, then we can predict it, and then we can make informed decisions about what to do with it. Anyway, I hope you're staying safe. I hope you're staying well. I hope you're using your time wisely, and I hope we can all see each other again real soon. Have a good day. Bye-bye.